All right, so we're back. I realized that Zoom had an update right before I started recording this thing. So the normal way that I kind of hit like stop record and then bring it back had changed slightly. So you might have just saw me weirdly staring at the screen for like 8 seconds before I realized what button I now needed to hit. So hopefully everything is now a go again. I see the record probably working. So we'll check later on. So anyway, from the last video, I mentioned this kind of initial question of this search learning with error problem. So we're going to now jump into a cute little number version of that thing. So here I'm going to start off things with, pretty small values just because I'm lazy and I don't want to write out massive things. And then we'll jump into some code to see these things a little bit larger. So what I want to think about is what all is going to be publicly available for us to work with. I'm going to have an underlying prime. So here I'm going to have the number 17 as my little Q value. I'm going to have A become an n by n matrix. So here you can see that A is a 4 by 4 matrix. It's going to be filled with a bunch of those numbers modulo 17. So here you can see that I have LEET, so 1, 3, 3, 7. And then a 42, so the meaning of life, split into a 4 and a 2. I got Mr. Rogers' favorite number of 143 split into a 14 and a 3. And then I have Jenny's phone number, so 8675309. And then I needed one extra term, and I wanted something that, was also another double-digit number, so I just threw a 16 in there. 16 is not cute, other than it's the biggest number I can possibly put in there, so I shoved it in there as well. So A is totally publicly available. It's randomly generated, but here I, threw some numbers that are not so random, but I don't know if they're easy enough to look at. And then we're going to have one of these samples. So B is then going to be generated kind of off in the background by taking some unknown vector S, which is going to obviously have 4 entries in it, as well as some other unknown vector E. And we're going to compute this thing by taking S times A and then adding E to it. So again, the picture of what's happening is that S times A is going to land me at one of these lattice points. And then when I add E to it, it's going to wiggle away from it just a little bit. So our goal is then basically to think about what S and E possibly could be. All of the arithmetic here is then going to happen modulo 17. So we're going to kind of just be thinking in the background that anytime I see a number that's larger than 17, obviously that's going to start getting reduced down. So if you're going to see these things like a 12 as a back end side of things, but that 12 could have multiple 17s added to it or multiple 17s subtracted from it. So realize that that's going to be part of the swirly game that makes things somewhat interesting. Just because I think it is sometimes valuable to kind of remember where some of these things all come from, we can actually take this thing, which is currently written as one of these little matrix equations. So it's vectors times matrices, kind of giving me this one single equation. And I can blow this thing up into 4 nice little equations, basically do the actual arithmetic. So just kind of a reminder of how some of these things work. If I have this little vector and I'm going to multiply it by this matrix A, what it's going to kick out is it's going to kick out another vector. And the way that's done is going to be taking that little row vector that we have out on the front side and then do the twisty multiplication. So you're going to twist it and start to see those things emerge fairly nicely as well. What's going to happen is that it's going to do a kind of a weird little twist. So obviously the first entry in that new vector is going to be S1 times 1 plus S2 times 4 plus S3 times 8 plus S4 times 3. So you get this large entry that's all in that first slot. You're then going to add an E1 to it, which is just a number. And then I'm going to claim that that's going to be equal to 12. So that becomes what your first slot is, at least what your first, thing is supposed to be equal to. You're going to have 4 total versions of that, which you can then normally just plant into a nice little just collection of equations. So notice that there's a little bit of twisting that happens. So the 1, 3, 3, 7 is no longer across the top, because the twisty multiplication is going to take this thing and that thing, which is where that first equation is then going to come from. So just to kind of double check when you're working with these vectors by working with row vectors, things get kind of funky, but oh well, we've been dealing with it so far, so we'll continue dealing with it as well. Later on, we'll obviously bring in some transposings and start twisting some of these things, so we'll see it all come full circle. So in any event, this question basically boils down to us looking into this system of 4 equations with 8 total unknowns. There's technically a few more like unknowns because, again, all of these equations are written modulo 17. So you could think about each of those equations being equal to like 17k or 17k1, 17k2, 17k3, 17k4, if you wanted to see kind of how many multiples of 17 you're going to have on the backside. So there's all sorts of kind of over identification of stuff, which means that there might actually be multiple solutions to this. In fact, for this system, we will end up having multiple solutions, but it's one of the things that we want to kind of keep in the back of our head, obviously. So if I present this into my not chicken scratch version of it, I have hopefully the exact same equation that we had before. So our question basically boils down, can we find a solution? And if we can we find a solution whose values are somewhat small? So again, the length of the vector is already going to be set. I know that each of these things are going to have 4 entries in them. I would like those entries to be somewhat small. Obviously, they're all going to be numbers modulo 17. So I have ranging from 0 to 16, but I'd like them to be kind of small, like 0s and 1s or 2s or something like that. Later on, when we build crypto systems, we're going to have hard caps for how large those numbers can be. So our quest right now is to try to do this, but also to keep things nice and tight. So here I'm just going to present it to you. So do you see any solutions to this system? Hopefully it's not super obvious as to what they're going to be, or this whole game breaks down. Or if it is super obvious to you, then we're going to have to like increase it to like a 10 by 10 system or something much worse, so that hopefully I can just break some intuition, I guess. So if you look at this thing, you maybe would have some chance to kind of untangle some of it, but I don't want to sit here and look at a blank computer screen while you maybe think on your own. So if you want to pause and just try your, have a go at it, you totally can. Otherwise, next I'm going to start giving some hints, and then maybe that'll untangle some of our solutions as well. So my first hint is going to be, I can tell you what some of the S values will be. So we're actually going to have at least a couple solutions for this one. So we're going to hone in on the first solution right now. So what I'm going to claim is that the S being 0, 0, -1, 1 is going to then yield some solutions. What that does for me is that it basically kills off all of that stuff, because I'm claiming S1 and S2 are going to be 0. So then you start to see -1s go there and 1s go there. And hopefully very quickly, you can then see that the E1, E2, E3, E4, those allow us to very easily kind of, figure things out afterwards. I don't have to do a whole lot of thought, because the S3 and S4, those exist across all of those equations. So if I can start pinning some of those down, then the E is just going to, correct some of these things. So we got some learning with these little tiny errors that are then going to go into play. So if you look at that top row, hopefully you can start to see what's going on. So I have 8 times -1, which is -8. So if you take that -8 and add a 3 to it, you're going to have what? -8 plus 3 is going to give you -5. And my goal then would be to add something to that to make it into a 12. Again, remember that we're living modulo 17, so that -5 is actually 12 already. So hopefully that leads me to seeing exactly what the E is going to be, at least for the E1, is that those two quantities already make a 12, so the E1 doesn't have to do anything. So I can just set that to be a 0. Neat. All right, so let's keep on going down. So the next row is going to have the S3 still be -1, so -6 plus 0. So you would have -6 plus 0. If you wanted to view that modulo 17, that again is going to be an 11. So what do I need to do to get that 11 into a 10? I probably need to subtract a 1 or something like that. In the next equation, you'd have what? -7 plus 9, which is a +2. So here you can easily see that E3 would just become a 1 to make 2 plus something into a 3. I don't even need to do modular arithmetic on that one. The next one's going to be what? -5 plus 16, which is an 11. So I'm already there. So I don't need to take anything for E4. So that gives me one set of solutions. Obviously, the S and the E there are going to then work. If I wanted to try my hand at the other collection, hopefully you can see that by having the S's, my life is actually pretty easy. So if I'm taking this one to be a 1, this one to be a 1, and this one to be a 1, those all don't matter. So that top row, I'm going to have what? 1 plus 8 plus 3. So I'm already at 12 in that example. So my E's in both scenarios start with a 0. The next one's what? 3 plus 6 plus 0, which is putting me to a 9. So I probably need what? 1 more. The next one I have what? 3 and 7 and 9, which is 19. So that's obviously more than 17. So if I drop that down by subtracting a 17 from it, it leaves me what, at 2. So then I'm 1 shy. So I need a 1 here. And then my last one, I'm going to have what? 7 plus 5 plus 16. Again, I'm beyond the 17 because that's going to kick out 28. So if I remove 17 from that, it leaves me at 11, which is obviously exactly what I want it to be. So that puts me at a nice little 0. So you can see that we have a couple solutions. Both of those are, in fact, kind of small in terms of the weights that make them up. Officially, that top one is actually probably slightly smaller because it only has 4 total non-zero things, whereas the other one has 5 total non-zero things. The bottom one is only made with positive numbers, which is sometimes a little bit nicer, just because negatives are kind of annoying, but for a computer, they're obviously not going to matter at all. So you can get a couple of these kind of small solutions emerge. I think I have those written down. Hopefully they're the same. Oh, did I mess something up? I claim these are flip-flopped. 0, 1, -1, 0. Oh man, I probably did some kind of terrible arithmetic mistake on one of these, or the one I had there. All right, so let's go double check. Maybe there'll be some kind of quick edits to my notes. So this is the one that I'm claiming those were messed up. So that would have come from the middle row. So that would have been 0, 0. So -6 plus 0. So -6 is going to then what? -6 plus 17 gives me an 11. So that's definitely still supposed to be a -1. Okay, so I think my notes were just incorrect. So I'll make a note to myself to change those ones. And we'll pretend like it never happened, except for now it is recorded and absolutely obviously happened. So, oh well. What we're going to go next is we're going to try to bring in some of our old trickery kind of things. So I'll probably pause it here just to kind of make sure that I make note to fix my notes, as well as kind of set the stage for where we're going to go next. Hopefully you can kind of see that because we've been living in some of these lattice realms, we have some of these lattice reduction algorithms. So it seems likely that we probably can use some of those old tricks that we had before to possibly find some of these small little vectors. This world is no different. We're going to have a slightly larger matrix M. We'll still be able to hit it with this lattice reduction process, and then we'll go from there. So I'm going to pause it and we'll come back. So I will have this thing showing so that we can go from there.